Hey Wheaton North, Mr. Igler here. This video is going to get into galvanic cells. This is one of the most crucial parts of electrochemistry. You have to be able to identify all the different parts of the galvanic cell. It's very foundational to electricity, really, because this is how batteries, virtually every battery is made this way. So let's dive in. There's two types of electrochemical cells in general. Now the galvanic cell that we're going to do right now is just one of those two. Sometimes this is referred to as a voltaic cell. I'm going to call it a galvanic cell. In the galvanic cell, it's a spontaneous chemical reaction, and that chemical reaction involves the transfer of electrons. And so if we can capture those electrons or measure them, then we can use them to do something like power a light bulb, for example, right? So it's a chemical reaction that happens on its own, and that's driving an electrical current. That's creating an electrical current. The electrolytic cell, notice the difference in the picture, right? This is hooked up to a power supply because an electrolytic cell is taking a reaction that wouldn't normally happen on its own and forcing it to happen by applying an electrical current to it. So it's electricity creating chemistry as opposed to the galvanic cell, which is chemistry creating electricity. You could even have a galvanic cell that is hooked up to drive an electrolytic cell. All right, so let's talk about how these galvanic cells work. I'll talk through an example, and then we'll go through another example, and I think that'll be be the best way that you can understand how these are working. We have two different metals. We have zinc, a solid zinc electrode, and that's in a zinc nitrate solution, some sort of salt solution that involves the zinc ion. And then we also have a copper electrode that's sitting in a copper nitrate solution. Again, a salt solution that contains the copper ion. It could be copper sulfate, it doesn't really matter. Now, one of these two metals is more reactive than the other, right? Think back to single replacement reactions. Zinc is more easily oxidized than copper, or we could say that copper is more easily reduced than zinc. And so copper is essentially pulling electrons towards itself more than zinc is. Zinc would rather give them up, so to speak. And so if we connect these with a wire, then copper is able to pull electrons from the zinc, essentially. And when the zinc electrode loses electrons, at that surface between the metal and the solution, those zinc atoms are going to be losing electrons. The electrons are going to be traveling up the zinc bar and through the wire. And the zinc atoms are going to be going into solution, going from zinc to zinc ions. Meanwhile, those electrons are traveling through this wire, and they come down into this copper bar, and here we have the gain of electrons, or reduction. So we're kind of doing the opposite. We're taking ions out of solution, and we're giving them 2 electrons in this case, and forming a solid copper atom on the surface of that electrode. Now over time, this continual pull of electrons over to the copper side would make this side of the system kind of build up a negative charge. And that's where the salt bridge comes in. The salt bridge helps to keep that buildup of charge from happening. So negative ions from the salt bridge are going to go this way, and positive ions are going to go that way. And the salt bridge can be made up of a number of different things, usually some sort of inner salt, sodium chloride, potassium nitrate, something that won't interfere with whatever's going on. We just need to be able to move some ions from one side to the other to keep that buildup of charge from happening. So from here we could write our half reactions. On the zinc side, we're oxidizing, so we're going from zinc solid to zinc ions. And on the copper side, we're going from ions to solid, so that's reduction. So the electron flow is going from the left to the right. And if we put the two reactions together, we would have an overall reaction where we're going from zinc solid with copper ions to zinc ions with copper solid. This is essentially just a single replacement reaction with the spectator ion kind of removed. Now, because we're moving electrons from one side to the other, we're actually going to affect our electrodes. Over time, the zinc electrode will get smaller because it's losing its atoms into the ionic solution. And the copper electrode will get bigger because ions in solution are basically plating onto the copper electrode. So there's multiple things that you need to be able to know and identify. First, you need to figure out the half reactions in any galvanic cell. And with that comes identifying what's the cathode and what's the anode. Essentially what's getting oxidized and what's getting reduced. You should be able to calculate a voltage of the cell and figure out the direction of electron flow. That kind of goes with the half reactions. What's gaining electrons, what's losing electrons. We also need to be able to identify which electrode is gaining mass, which is losing mass, and with that, which solution is increasing in concentration and which is decreasing. And finally, what direction are ions moving in the salt bridge. So these 7 things, if you can do these 7 things on any galvanic cell, then you're good to go. So let's go through an example. We'll take a few of these at a time. Let's look at the tin and silver galvanic cell. In order to figure out what's the cathode and what's the anode, we need to figure out what's being oxidized and what's being reduced. The easiest way to remember this is that reduction is always going to happen at the cathode. They both start with a consonant. And oxidation is always going to happen at the anode. They both start with a vowel. So if we figure out what's being oxidized and what's being reduced, that tells us what's the cathode and what's the anode. For this, we're going to need to go to our reduction potential sheet. So let's find our two half reactions. Now this is a standard reduction potential, so they're all written as reduction. Notice that they're all plus electrons. They're all gaining electrons. Obviously, we don't always have reduction. We also have oxidation. And so you have to pay attention to what's being oxidized because you actually have to flip that one. So let's find our two half reactions. They're going to be silver and they're going to be tin. Now this effectively acts as an activity series. The higher up on the list it is, the more likely it is to be reduced. And so because silver is higher than tin, the silver is going to be the reduction half reaction and the tin is going to be the oxidation half reaction. So the silver is written as shown on the reduction potential sheet, but the oxidation we need to flip. And with that, we've now figured out what's the anode and what's the cathode. All right, now we need to figure out the voltage and the direction of the electron flow. Again, back to the reduction potential sheet. The reduction potential of the silver is 0.8, and the reduction potential of the tin is negative 0.14. But in our case, this isn't a reduction half reaction, it's an oxidation half reaction. So it's actually going to be positive 0.14. So now we can add those two together, and our voltage of our overall cell is going to be 0.94. And with figuring out the half reactions and what's gaining and what's losing electrons, now we know that the electrons are going from the tin because they're being produced here and they're being gained over here. One thing I forgot to mention is that notice that the tin is producing 2 electrons and the silver is only gaining 1. If you were to put those two half reactions together, you would have to double the silver, the reduction half reaction, so that the electrons cancel out. All right, now let's figure out the electrode mass change and the solution concentration change. The tin is going from solid to aqueous, right? So it makes sense that this one would be decreasing in mass. The atoms of tin are going to be going into solution, and so that electrode is going to get smaller. Meanwhile, on the opposite side of the cell, it's going to be the opposite, increasing in mass over here. We're taking ions out of solution and we're plating them onto the electrode. Remember this picture from earlier. Those ions are getting reduced to form neutral atoms on that electrode. Now what about the solution concentrations? Well, if the tin is dissolving into solution, if we're going from solid to aqueous, then it makes sense that this solution is going to be getting more concentrated, right? And similarly over here, we're plating ions onto the electrode, and so that's going to be decreasing in concentration. Finally, the direction of salt bridge ion flow. So this salt bridge, I'm not really showing this here, but it has all kinds of ions in it, right? Positive and negative, because it's like sodium chloride or something like that. Which direction are the ions going to go? Pay attention to where your electrons are going. Since they're going from left to right, we're going to have a buildup of negative charge over here if we don't cancel that out by sending positive ions to this side. Similarly, as you're losing all those negative electrons through your wire, you need to replenish those negative ions and that negative charge by sending the negative ions to the left. And this will keep the reaction going. As long as we can keep replenishing that charge, then the reaction can continue. Eventually you run out of something, right? You either run out of solution over here, or you run out of metal over here on your electrode, or you run out of ions in your salt bridge. Eventually it has to stop. But the more we can keep replenishing that charge, the better off it's going to be, the longer your battery is going to last. So that's everything you need to know with galvanic cells. If you have any questions, make sure you write those down. And this is Mr. Yurgler signing off.